네, 안녕하세요. IT 전방송 토크 IT 제작꾼 CPD 고소입니다. 오늘 요즘 이제 굉장히 큰 화두이죠. 애플, 삼성전자, 또 샤오미까지 모든 스마트폰의 메이저 회사들이 다 요새 눈독을 들이는 기술입니다. 네, UWB, 울트라 와이드밴드. 요것이 도대체 무엇이길래 이렇게들 다들 이렇게 여기다가 이제 관심을 갖고 있고 여기에 이제 큰 또 이제 투자도 많이 하고 있는지 이런 얘기도 이런 것들이 도대체 그렇게 좋은 거라면 이거를 그러면 우리는 이걸 만들 때 어떻게 측정을 해야 되는지 네, 이런 얘기들을 한국 로데슈바르즈의 이성원 매니저님 오늘 게스트로 모셨습니다. 안녕하세요.
안녕하십니까.
네네. 자, 매니저님 오늘 이제 우리가 이거 더 딥하게 들어가기 전에
네.
측정 그런 거 얘기하기 전에
네.
그거보다 일단 UWB가 뭔지
네네.
그러니까 제가 조사해 보니까
네.
얘가 최근에 나온 기술이 아니라
네네.
나온 지 꽤 됐더라고요.
네네. 기본적으로는 군용으로 많이 사용을 되었었던 기술이고요.
네.
2000년대에는 그 이제 무선 USB 기술을 대체하기 위해서 사용이 되었는데 당시에 이제 와이파이랑 이 UWB가 이제 서로 경쟁 상대였었던 거죠.
밀렸구나 와이파이한테.
네, 와이파이는
왜 밀렸어요 와이파이에?
와이파이는 기본적으로 이제 인프라가 많이 갖춰져 있었던 거죠. 칩셋 회사도 많고 사용하는 기술도 많고 뭐 이래서 근데 상대적으로 UWB는 인프라가 너무 적었던 게 지금까지도 이제 인프라적인 문제가 단점이 되겠죠.
근데 우리가 울트라 와이드밴드잖아요.
네네네.
도대체 데이터를 얼마큼 보낼 수 있길래 울트라 와이드라고요?
저희가 이제 흔히 사용하는 블루투스는 1메가의 대역폭을 사용을 하고
네.
우리가 LTE도 뭐 20메가 그리고 뭐 5G로 가더라도 한 셀 기준으로는 FR1 기준으로 100메가의 밴드위스를 사용을 하는데 UWB는 500메가의 대역폭을
500메가?
네.
와.
500메가의 대역폭을 사용하기 때문에
네.
UWB라는 용어를 이제 기본적으로 사용을 하고 있는 거죠.
자, 근데 이렇게 와이파이 밀려가지고
네네.
변방에 있던 것들이 있는 기술이 왜 요새 와서 이렇게 갑자기 또 와 이렇게 된 거예요? 계기가 뭐예요?
이제 아까 이제 말씀드렸던 것처럼 인프라적인 요소가 큰데 애플이라는 큰 회사에서 UWB라는 기술을 U1이라는 칩셋을 통해서 지원을 하기 시작했고
아이폰 11서부터?
네, 11에서 에어드랍이라는 기능에 U1 칩셋을 사용해서 UWB 기능을 사용을 했던 거죠. 네네. 그리고 지금 최근에는 올해 이제 적용되어 있는 삼성 안드로이드 계열에 있는 삼성 갤럭시에서도 이제 적용이 되어 있습니다.
자, 근데 궁금한 게 UWB 이렇게 제가 뭐 이렇게 조사해 보면 얘가 어떤 아까 많은 데이터를 500명 보낼 수도 있지만 얘가 거리를
네네.
거리가 아닌 위치지.
네.
정확하게 어디에 위치하는지를 굉장히 정확하게
네네.
몇 메타가 기준에 몇 센티미터 기준으로
네네.
정확하게 파악을 한다 했거든요.
네네. 기존에 다른 기술들은
네.
미터 단위의 아큐러시를 가지고 있는데 UWB 기술은 이제 그 내부의 TOF나 AOL이라는 측이 기술을 사용을 해서
네?
이제 그 센티미터 단위의 아큐러시를 가지게 되는 거죠.
아니 근데 얘가 보면 제가 오늘 오면서
네.
UWB 관련된 유튜브를 들어오니까 이것의 적용 기술 중에 하나가
네네.
자동차 키지 않습니까, 요새?
그렇죠.
자동차
네.
키에
네네.
앞으로 얘가 그걸 대체하는 세상이 올 거라고 하면서
네네.
얘를 쓰면은 내 운전자가 여기에 어디에 앉아 있는지, 자동차에
네네.
어디에 앉아 있는지 위치가
네네.
정확히 안다 그랬거든요.
네네네.
네.
그 이제 인도 내비게이션에서 센티미터 단위로 측의를 할 수 있다라는 것은 저희가 이제 있는 위치를 좀 더 기존에 이제 미터 단위가 아니라 좀 더 이제 세밀하게 확인할 수가 있는 거죠.
아니 보통 우리가 그 밖에서
네네.
이렇게 위치 측정할 때는
네네.
스마트폰도 그렇고 요새 보면 다 GPS로
네네네.
결국 GPS로 삼각 측정을 하는 거지 않습니까?
네네, 맞습니다.
그러면 얘도
네네.
UWB도 그러면 이제 인도에서 GPS 안 쓰고 없는
네네.
데서도 얘가 그러면 얘도 뭐 삼각 측정하는 걸 하는 겁니까?
그렇죠. 기본적으로 TOF라는 거는 그 시간 정보를 가지고 있기 때문에 신호를 보내고 받는 시간 정보를 가지고 거리를 계산을 하고 AOL이라는 기능은 안테나 2개를 가지고 삼각 측정을 하셔 정확한 이제 방향까지 잡아내고
네네.
그러면 거리와 방향이 나오기 때문에 정확한 측의를 할 수가 있는 거죠.
그럼 얘가 어느 정도 거리 안에 레인지 안에 있는 것을 이제 위치를 측정할 수 있는 겁니까?
네네.
어느 정도 범위?
통상 100m까지도 가능하고요.
100m까지.
네. 근데 일반적으로 이제 10m 단위 이제 인도도 이제 가능을 한 건데 중간에 있는 이제 혹시나 예를 들어 애플폰이 하나가 있고 중간에 또 다른 애플폰이 있으면 같은 기술을 사용을 하고 있는 애플이라면
네네.
이 거리만큼 또 늘어나게 되는 거죠.
네. 요새 보면 스마트폰에서 이렇게 무선 태그라든지
네,
해서
그렇죠.
내가 어디 있는지 그 태그만 달면
네네네.
스마트폰에서
네네.
어딘지 쉽게 찾을 수 있다. 그것도 이 기술 쓴 겁니까?
그래서 애플에 있는 애플에서 나온 태그도 있고 이제 올해 이제 갤럭시에서 나온 태그 UWB가 적용된 태그도 있습니다.
네. 그러면 이제 결국 UW로 통신해가지고
네네.
아까 같이 10m 이내면
네.
100m 이내면 찾을 수 있겠네요.
네네.
오. 이게 그러면 이게 결국 앞으로 이 기술이 여기 스마트폰에 다 들어가면
네.
얘가 단순하게 뭐 그 태그 얘가 모든 뭐 도어락이라든지 모든 거에 얘가 중심이 될 것 같은데요. 가뜩이나 지금도 중심이 되고 있지만
그렇죠.
스마트폰이.
예. UW가 추가가 됨으로 인해서
네.
UW가 활성화되는 인프라에 관해서 그 기능들도 다 이제 업데이트가 핸드폰으로서 다 처리가 되는 거죠.
네. 그렇다면 지금 이게 모든 이제 삼성전자나
네.
뭐 그 애플도 그렇고 샤오미도 그렇고 이런 스마트폰 하는 회사들 또 자동차 회사들
네.
이런 회사들이 여기 이 기술을 많이 좀 연구하고 있는 겁니까?
네. 그 삼성이나 애플에서 발표를 할 때
네.
자동차 회사들이랑 디지털 키를 협업을 하겠다라고 발표가 다 되었습니다.
그렇다면 지금 자연스럽게 이런 이제 뭐 삼성전자나 아니면은 뭐 자동차 회사의
네네.
1차, 2차 밴더
네.
거기들도 이런 걸 이제 뭔가
네,
좀
관련되어 있는 기술들을 당연히 그 업체에서도 지원하는 어떤 기능들이 이제 나오게 되는 거죠.
자, 오늘 이 갖고 오신 이 장비가
네.
요게 이제 그럼 UWB를 이제 연구하거나 만드는 회사들이
네네.
그거 할 때 이 장비로서 뭘 하는 겁니까?
UWB를 이제 그 IEEE에서 UWB를 사용하기 위해서 얘는 어떠한 측정 방법을 통해서 어떤 항목을 검증을 해야 된다라는 그런 항목들이 있습니다. 그런 항목을 검증하는 장비라고 보시면 됩니다.
아, 네.
네.
자, 근데 그걸 검증하는 데 있어서
네.
로데슈바르즈가 어떤 점이 로데슈바르즈에 그걸 할 때 가치를 주는 거예요? 좋은 점이.
네. 이 장비는 이제 기본적으로 UWB 기술이 현재 이제 TOF나 AO에 관한 기능이 이제 중점이 되고 있는데 그 모든 기능들을 이 장비 하나로 다 측정을 할 수가 있는 거죠.
알겠습니다. 자, 여러분들 이제 UWB가 뭔지는 이제 본질은 아셨을 거고요. 자, 그러면 이제 여기 또 실무자분들이 계시니까 실제로 UWB를 이거를 어떻게 제도 측정하는지 기술적인 얘기들 직접 로데슈바르즈 본사의 전문가분께서 얘기하신 거를 저희가 이제 영상 자막 한글 자막 해가지고 한 50분 좀 넘습니다. 50분 되니까 그거 들으시면서 궁금한 거 있으면 댓글 달아주시면 직접 오늘 이성호 매니저께서 이따 답변해 줄 거니까 여러분들 궁금한 거 편하게 질문해 주세요. 자, 영상 보실까요?
Hello everyone and welcome to our webinar. Thanks for joining. Today we want to talk to you about the challenges to test ultra-wideband technology in development and in production. My name is Martina Neuherz and I work for the market segment Automotive based in Munich at the headquarters. Let's start with a look at the agenda. First of all, I would like to give you a brief overview about technology, standards, and market size. Then I explain to you the automotive applications which are relevant in this area. Then we have a brief look at test requirements, followed by system solutions for R&D and production. Well, ultra-wideband technology is a short-range, high-bandwidth radio technology operating in unlicensed spectrum that enables a near-field, low-power consumption communication with low complexity and low cost of implementation. Since the transmission is timed to specific intervals, that means pulsed, ultra-wideband is fairly robust against narrowband channel fading and interference. It's a technology that is using a 500 megahertz channel in the 3.1 to 10.6 gigahertz range. This also prevents the so-called man-in-the-middle attack. Because ultra-wideband leverages pulse transmissions at specific time intervals, the system can use the transmission information to determine time of flight and angle of arrival information. Time of flight is basically the signals traveling between the initiator and the receiver, as it is shown on the graphic on the right side. Well, although ultra-wideband is actually one of the oldest wireless technologies, it has been showing steady market size growth within the next years. Ultra Wideband Alliance estimated that 80% of the smartphones related to accessories and 11% of car access devices will be equipped with Ultra Wideband technology by 2025. Specific advantages are the accuracy and detection performance in combination with a high security level, low power consumption, and the excellent robustness in wireless connectivity. We are looking back at 20 years of ultra-wideband communication and precise ranging. The standard was firstly defined in 2002 by the Federal Communication Commission. After that, the IEEE took over and defined several versions of further standards. For the automotive industry, especially the last one of 2020, the 4Z is important. Furthermore, we have quite a lot of stakeholders in this technology area. For instance, the Ultra Wideband Alliance, which was founded in 2018. The Ultra Wideband Alliance is dedicated to the promotion and growth of the ultra wideband ecosystem. It supports large-scale deployment of ultra wideband technology while fostering cooperation with interoperable specifications and standards. Furthermore, we have the Fiera Consortium. It's an organization which was founded in 2019, who is dedicated to grow ultra-wideband applications by ensuring interoperability between multiple devices. Fiera is focusing on 3 core topics, which are hands-free access control, location-based services, and device-to-device services. By the way, Rohde & Schwarz is an associate member in the Fiera Consortium. Omlox is an industrial open standard that harmonizes all the existing positioning technologies, like ultra-wideband, Bluetooth, low energy, RFID, 5G or GPS through a common standardized interface. What's also important for the automotive industry is the Car Connectivity Consortium. It's a global consortium of the automotive industry. One of the Car Connectivity Consortium's mission is to specify a standardized interface between the vehicle and the smartphone to ensure a consistent user experience and increased operability. Therefore, the Car Connectivity Consortium is currently working on a digital key release 3.0 planned with ultra-wideband and Bluetooth technology. Let's have a short look at the technology. On the left-hand side, you can see Bluetooth, respectively Bluetooth Low Energy, GFSK modulation. In principle, the frequency domain of Bluetooth is more or less a single frequency, just 1 megahertz wide at 2.4 gigahertz spectrum. If we look at ultra-wideband, we see these very short pulses of 1 to 2 nanoseconds, which result in this very wide spectrum of about 500 megahertz. And we are talking about a frequency range of about 6 to 10 gigahertz. Also, the power density is interesting. Bluetooth uses 20 dBm per 100 kilohertz, AIRP, in contrast to ultra-wideband with minus 41 dBm at 1 megahertz. With a very strict power spectral density of ultra-wideband, it is ensured that this technology will not interfere with already existing wireless systems in the given band. So let's look at the channel allocation. The IEEE standard defines 2 physical layers. One layer is for low pulse repetition frequencies, so-called LRP, of 1 megahertz to 4 megahertz. The other layer, mainly used in today's applications, work with high pulse repetition frequencies, HRP, ranging from 4 megahertz to 250 megahertz. However, the majority of applications using the defined high-band channels in the range of 6 GHz to 10 GHz with a channel bandwidth of 499.2 MHz. The automotive industry focused on channel 5 to 9. Channel 9 is mandatory. The IEEE is a standard which was first released in 2003. Defined for low-rate wireless personal area network targeting at low complexity devices. After the time, this standard was further developed, and the latest version is now the 4Z version, which was published in 2020. 4Z is an amendment to the version of 2015 that enhances the HRP and LRP ultra-wideband physical layer in terms of power consumption and also security aspects. The 4Z version also improves the media access control layer to support the control of time of flight ranging procedures. Furthermore, high-rate pulse repetition frequency was introduced. For this webinar, HRP ultra-wideband based on 4Z will be addressed. This is a testing solution technology webinar. A basic ultra-wideband technology introduction has been provided by our previous webinar. It focused on the evolution of the ultra-wideband standard, ultra-wideband certification needs, communication technology, as well as general testing requirements. It might be helpful to follow up to this webinar. It's accessible via the Rohde & Schwarz website at any time at your convenience. Ultra-wideband enables secure ranging applications in many industrial areas. It's suitable to locate assets to a precision down to 10 centimeters. With this, ultra-wideband enables use cases such as secure hands-free access to locations, for instance, workplaces or hotels. It enables mobile payment or asset finding by using a dedicated tag. In addition, ultra-wideband can be employed for everything around augmented reality or so-called virtual reality, as it is mentioned here. Currently, all major smartphone vendors provide ultra-wideband technology. Ultra-wideband is becoming a hot topic in the automotive industry. With ultra-wideband, users can open and start the car while leaving their phones in their pocket or bags. The technology can be used as a kind of radar, let's say, for gesture control, for instance, to open the car trunk. Cars can be sent to park autonomously via smartphone using ultra-wideband based indoor navigation. Based on ultra-wideband, you can also control the child seat positioning or the correct trailer coupling. And even more, with ultra-wideband, you can share access credentials over the smartphone and grant temporary access to other persons, for example, your colleagues, or to in-car parcel delivery services. However, the keyless access system is currently the main topic of interest in the automotive industry. This feature will firstly be launched by BMW in its new electric iX car. Other OEMs like Tesla, Daimler, and also BMW are working in this area as well. Let's proceed with the ultra-wideband test requirements. So what are the typical measurement requirements for HRP ultra-wideband applications? Well, more or less, it's usual requirements that we know from all wireless technologies, which are defined by the IEEE. Probably some are a little special, let's say, because it's a pulsed communication. On the right side, you can see some additional measurements that were defined based on customer feedback. This also covers time of flight and angle of arrival measurements. In the next part, we will explore the different test solutions Rohde & Schwarz can recommend to you. For this, I have Werner with me. Werner, you're an expert for signal and spectrum analysis. Can you please explain us the different test application areas and the most suitable methods to test ultra-wideband in the early stage of a product development?
Sure. Hello, my name is Werner Düppert. I'm product manager and in charge of measurement applications for the analysis of wireless non-cellular signals as ultra-wideband. If we talk about test solutions, we would have to talk about application areas at first. Depending on the application area, specific criteria have to be fulfilled, like set and speed of measurements, accuracy, performance, maybe size, and last but not least, also the price level of the measurement equipment itself. Of course, deciding for a specific test solution is not a black and white decision. Typical test and measurement devices can be also used in different application areas by an overlapping of features and functions. Important for ultra-wideband measurements and applications is that essential measurements are supported by the test and measurement equipment in accordance to the related IEEE standard. Besides application areas, quality assurance and verification or production, with the following slides and a short demonstration today, I would like to focus on test solutions for research and development. Typical test and measurement applications will be measurements on modulators or transmitter modules, on receiver modules, on amplifiers, and also on complete modules, which consists on receiver part and transmitter part. For all these measurements and scenarios, dedicated measurement equipment is necessary. Here, we recommend the use of an ultra-wideband signal generator and ultra-wideband signal analyzer. In some cases, also an all-in-one test and measurement equipment would be beneficial for testing of modules, for example, where time of flight measurements or angle of arrival measurements has to be done. And sometimes an all-in-one solution offers more comfort for the setup and some other features which are very helpful for such kind of measurements. So for today, I like to introduce some test and measurement solutions. So for the generation and analysis of ultra-wideband signals and a piece of software. Let me continue with the signal generators. So on this slide, you see two models. One model is the SMW200A, and another one is the SMM100A, a smaller version of the signal generator. Both signal generators cover the frequency range from 100 kHz up to 12.75 GHz, which means that every ultra-wideband bands can be generated. Essential differences can be seen in the modulation bandwidth. So the SMW supports modulation bandwidth which is up to 2 GHz, which means we can generate signals of mandatory and optional ultra-wideband channels. So the SMM100A, the smaller one, has a modulation bandwidth of 1 GHz, which means the generator is able to generate signals of the mandatory channels and so not for the optional channels. So the SMW has additional features. So for example, by fading option, one is able to simulate also several scenarios with echoes and so on, and also noise generators inside so that we can simulate different configurations or impacts of transmission. And in the lower right corner, you can see also a screenshot of the WinEQSIM software. It's a piece of software which is able to generate waveforms according to the standard and parameters, waveforms which can be afterwards used also by the signal generators. So it's a very comfortable way to exchange also signals between several generators. So if you have to do some development work at different sites. So on this slide, our first test solution for the analysis of ultra-wideband signals. So here you can see our spectrum and signal analyzer FSW26. 26 stands for the upper frequency, which is supported by this model. That means every ultra-wideband channel will be covered by this analyzer. The analyzer can be equipped with different bandwidth options. So especially also for ultra-wideband, the B1200 option would be of interest, which is sufficient for the measurements and analysis of mandatory multi-wideband channels. And with the option B201, so this analyzer will have a demodulation bandwidth of up to 2 gigahertz, which is then also sufficient for the analysis also of optional ultra-wideband channels. They have seen it in some sites before, which can be up to 1.3 gigahertz in bandwidth. So benefits and key features of the FSW26 are an excellent phase noise characteristic and very nice low noise floor, a wide range of applications and standards which are supported, and of course dedicated measurement features, especially for the ultra-wideband analysis. So I have said so that the FSW supports several applications and standards. So it can be seen here on the left side. You can see the mode menu, which can be opened for the selection of several standards and measurement features. So, for example, we have here applications for a real-time spectrum analysis for a bandwidth up to 800 megahertz. We have here dedicated measurements implemented for the amplifier testing, and also, for example, also a measurement application for phase noise measurements. So phase noise measurements would be also of interest. So if you have to prove the quality of modulator, and also phase noise has an impact also on measurements or functions like time of flight or angle of arrival. But the essential function, of course, is the application which supports ultra-wideband measurements. So for that webinar, I have prepared already a short demonstration, so in practice, so that you can get a first impression how signals can be set on the generator side and how ultra-wideband signals can be analyzed with an FSW in this case. So if you set a signal for the ultra-wideband, you have to start with the frequency. So we have here 7.987 gigahertz. Then after the frequency, you have to describe the signal itself. Here from the standard list, we select ultra-wideband, the standard. In the mode menu, we decide for the high pulse precision frequency mode. And so we have here the most important parameters. Channel 9 will be in accordance to the selected frequency. And in the next step, we have to take care on the signal parameters of the frame configuration. So by graphics, you can see the arrangement of the different packages which can be defined. So here, for example, if we decide for mode 2, so the payload would be before the scramble packages. But here in this example, we select the package mode 1, where the payload is at the end of the frames. Code index can be selected. Here, as an example, we select number 4. Then for the synchronization part, so we keep the default values as they are. Then in the data section, so you can see we have here as a data source several possibilities. We can select different randomized sequences. Here we select PN9. Evolutional code could be selected. And also we have here the possibility to change the data rate. We select a higher data rate of 27 megabit per second. Data length can be selected, which is in this case not so important for this example, but here you can select, for example, 30 octets. And here by pop-up menus, you will see also always the minimum, maximum values which are possible to fill in to guide you a little bit. Here the scramble part can be also filled in and in the flexible way configured, but it's not important. So if you go back now to the general part, so you have here the overview, what we have selected. And before we can do the measurement, we have to activate the signal. And last but not least, also we have to switch on the RF stage for the generation of the ultra-wideband signal. So it was a short example how easy and how structured a signal, an ultra-wideband signal, can be generated. But so we have now to take care on the other side of life, or in this case of technology. That means we have to take care on the analysis of ultra-wideband signals. And also for that, I have prepared a short demonstration how ultra-wideband signals can be analyzed. Here you can see now the user interface of a FSW, so where in the mode menu several applications can be selected. I talked about real-time spectrum analysis, amplifier measurements, dedicated ones, so we can also analyze several other standards, but here in this case we have to select ultra-wideband measurements or the measurement application. So if you start the ultra-wideband application, you will see an arrangement of several measurement windows which can be configured. But before we start with the measurements, we have to take care on the signal and on the configuration of the signal. So for that, I go to the signal capture menu. I select the channel 9 as selected before on the generator side. And with information, so I have to set the center frequency of the spectrum analyzer and analysis part. And you can see already the first captured signals and so, but we have to do something still for the analysis. And here in the lower line, you can see also which kind of channels will be supported in this mode. So if you now go to the emulator configuration, so we have to do some adjustments. So we have to select now the 4Z standard, the higher data rate as before on the generator side. And here you have seen it before. We have also selected the packet format to the mode number 1, where the payload is at the end of the frame. But we have still flashing values. That means we have to do a little adjustment here for the capture time. So by a slightly increasement. So to 2 milliseconds. And after that, so we have now stable measurement values. And the FSW is now ready for the analysis of the ultra-wideband signal. So we have here several windows, as I've seen before. So let me introduce the first window. So we have here the packet insights, which gives you the main important information about the characteristic of the signal, so that you can be sure that you have selected the right one by code index and some other parameters. The most important measurement screen, which offers values and tickets, is the result summary, which is structured in several parts. So the first part will reflect parameters on the frequency, the second one on jitter. So correlated pulse section will give you information regarding quality of the modulation itself of the pulses. Here, in case of failures, this will be indicated here in the list. And at the end of the list, we have here some other quality parameters like EBM, but also power values for each portions of the ultra-wideband frame and some ranging information regarding timestamps. So depending on your measurement task, you can configure the measurement screens by your own. So here is a very easy way. You can select one of the measurement screens. Here, for example, the packet spectrum could be of interest, which can be just added from the list in a very easy way. And in addition, so we will choose another measurement here. Yeah, let me see. Simple time jitter measurement, which gives you also some information about the accuracy of the signal, which has also an impact on the time of flight measurement. Each of the measurement windows can be expanded. Here by the time jitter measurement, you can see here the statistic and the variation of the measurement values. And here for the spectrum, which gives you the complete bandwidth of 2 gigahertz, the spectrum together with the spectrum emission mask. Here you can control if everything is fulfilled according to the IEEE standard and mask. Here we have a green pass indication. And so it's very easy to perform these measurements this way. So you have seen how flexible the measurements can be configured. And so according to your needs and how easy it will be to dealing with this application for ultra-wideband. So for the analysis of ultra-wideband signals, the FSW26 with its dedicated ultra-wideband analysis application is one way for the analysis, or one solution for the analysis of ultra-wideband signals. Another solution will be the use of one of our scopes. So on the next slide, you will see the RTP, which is a high sophisticated oscilloscope for the analysis of signals. And here we have to reflect on dedicated advantages, which comes with an oscilloscope compared, for example, to a spectrum analyzer. So typically, or here especially, the RTP supports a wider range of trigger possibilities, and so on the complete frequency range, and something more which could be of very interest and advantage if you have to dealing with pulsed signals. So from the standard, or as a standard, the RTP supports already the bandwidths of the ultra-wideband signals for the mandatory signals channels and also for the optional channels. So one essential advantage of the scope is here also that the scope is equipped with several RF inputs. Here in this case, we have here 4 RF inputs in parallel, which are coherent to each other, phase coherent, which gives some advantages for some other measurements, which will be introduced on the next 2 slides. And here for the scope, we have also here developed a piece of software. We have the general vector signal analysis software, VSA. And for this VSA software, we have also developed and offer now an ultra-wideband application, which offers similar measurements as seen before by the FSW. So if you are talking about phase coherent RF inputs, then we have to reflect to one of the important measurements, which can be done on the level of modules. Here, for example, it's here angle of arrival, where the estimation of the direction will be based on the difference in phase. And here it's beneficial. So if you have here phase coherent inputs, which offers also in addition some possibilities for settings and compensations of cable lengths, for example, and levels and so on in a very easy way. To have more than one RF interface in one device offers a further possibility or advantage. So on the left side, you can see here a device under test with different interfaces, one interface for RF, a bus interface and power interface. And in practice, so the interfaces could maybe have an impact to each other, and to figure out any problems. So the scope with several RF interfaces offers the possibility to arrange several measurements in parallel to see which kind of impacts to the signals and correlations can be seen here to figure out the source of problem. So with this slide, I would conclude my presentation. And yeah.
Thank you, Werner, for this perfect overview. Werner presented our solutions mainly focused on applications and R&D. Let's look at the specific application and its measurement challenges. For an insight in this, I hand over to our expert, Nicola.
Thank you, Martina. Hello, my name is Nicola Serda. I'm the product manager for the CMP 200. This Roland Schwarz instrument is capable of covering all the important measurements for the ultra-wideband physical layer. This would be the transreceiver measurements, the receiver measurements, time of flight verification and calibration, and of course, looking at the quality for the angle of arrival measurements. It is used all over the different stages in the process of creating an ultra-wideband device. Nevertheless, it's at the start with a chipset manufacturer or when the Tier 1 supplier is making their product. Nevertheless, it's in R&D or production. We have learned from Martina, the automotive industry has rediscovered the ultra-wideband technology for its use cases. One of them is the remote keyless entry application. Today, I want to talk about this specific use case, how it is functioning, go a little bit deeper into the technical details about the important setup parameters, and give also some hints how to improve the localization accuracy of ultra-wideband devices. To localize the things is the main application when we talk about the advantages of ultra-wideband in comparison to other technologies. Of course, it can also do data transmission, but we have also other technologies that can make this application happen. Therefore, the quality of ultra-wideband products will be judged how exact the localization will be determined by such devices. First, I will explain the technical details and then show a demonstration. I will show just a little bit of the TX measurement. It was already covered in, let's say, epic bandwidth. with my colleague Jörg and me. And today I want to show the tech mode with data decoding, both necessary features for the key fob. Let me just show you one slide about the capabilities of the CMP200 to be on the same page, that you know what we are talking about. And then I will go into more detail about the test and measurement challenges for the key fobs. In the right bottom corner, you can see the instrument we are talking about, the CMP200. It consists of an analyzer and generator. Of course, the general purpose measurements are coming out of the box. So it's an ARP generator. It can replay predefined waveforms or chipset specific waveforms or replay continuous waveform signals. The analyzer is an FFT spectrum analyzer. It can act as an IQ recorder, perform IQ with a slot, or the power measurements. The frequency ranges for the analyzer is 4 to 20 gigahertz, and for the generator, it's 6 to 20 gigahertz. As you can see, it's perfectly suited for the HRP ultra wideband physical layer measurements for band group 2, which goes from 6.5 to 9.5 gigahertz, including the important automotive channels, channel 5 and channel 9. Now let's talk a little bit about time of flight, especially the tech mode. On the left side, we can see the ultra wideband DUT. It's split in two parts. One part is the digital part of the ultra wideband DUT, and here we have the analog part of the ultra wideband DUT. And on the right side, there is our CMP200. In a real-life scenario, this would be the car. The key fobs will act as a tag, so it will initiate the whole messaging. It will send a poll message to the anchor, and starting with the counter of the T loop time. Then we will here have also a counter for the T reply time, and it will be sent back. The reason why we have splitted the DUT is because here we have the first improvement for the accuracy. The verification, the calibration of the analog interface of the DUT. We need to know how long the signal will take to cross the analog part of the DUT until it goes over the air or into a cable. So we have measured some devices, and we have seen that the analog interface delay could be somewhere between 1 or 2 nanoseconds. This would equal to an offset of 30 to 60 centimeters if we would not take this into account. Very important. In a conducted environment, we are making a single-sided two-way ranging. This is what you can see here. And our instrument would read out the T-loop number over the chipset of the DUT. In a real-life scenario or in production, the DUT would need to send a third message to the anchor. Also to correct error and the frequency error. This is another hint to take this in account, to take a third message, the double-sided two-way ranging. And in a real-life scenario, that the car also knows where the key fob is localized. This information is stored in the frame, more precisely in the physical payload. So we would need to decode the payload into a bit stream, search for the information of the T-loop number, and then translate them into a value. These frames can have different variations depending on which STS configuration you are taking. Of course, you would need to take one with a payload, or else you would not be able to perform this kind of application. So another hint. Speaking of OTA measurement and what it's important to take into account. In the right upper corner, we can see our calculation for the signal path from our combiner to the DUT. So our path goes from the middle of the combiner. Of course, we have to leave this combiner, so we have to take this value into account. We have measured it. For our coupler, it's 120 picoseconds. After that, there is an attenuator. Of course, we have to take this also in account with 100 picoseconds. Then there is the cable to the antenna. Of course, depending on how long is the cable, this value may be a little bit different depending on your test setup. And now is another hint. We are calculating then from the phase center of the antenna to the DUT and not from the start of the antenna. So the signal will leave the antenna from the phase center and not from starting point of the antenna. Here described with the parameter y. If you do not consider this, then you have again an offset here. For our Vivaldi antennas, we have measured and have taken the value of 483 picoseconds. How we got this value, I will explain on my next slide. Then there is the time of flight. We could say how long the signal needs from the phase center to the entry to the analog interface of the DUT. This is then calculated with the distance through speed of light. You can see that this is very, very important to take every possible parameter into your calculation, because if there is somewhere hidden 1 nanosecond of a delay that you have not taken your equation, then you have already an offset of 30 centimeter. Then the signal will enter the analog front end, will go through the analog front end, and then to the digital part of the DUT. So this is the path that you have to consider if you are using an over-the-air setup. And in my opinion, an over-the-air setup is the real deal, because it's the same as the real-life application. We have no cables. We are taking our antenna into account. We are taking the phase center into account. We take everything into account to make the best possible ultra-wideband devices. In the automotive industry, we have seen that the channels number 5 and channel number 9 being used. So channel number 5 is at 6.5 gigahertz and channel number 9 is at 8 gigahertz. In this graphic, you can see two different curves. One is the blue curve. So the blue curve represents the phase center, Y, how it's changing. Phase center always is changing depending on the frequency. It goes back and forth in the antenna. As we can see here, the difference between these two channels is not that great. So there is nearly no difference. We can also see here the delay that is resulting from it on the orange curve. So I believe this is orange. And we have taken the average from both points. So this would then equal 483 picoseconds to minimize the error. Of course, there would be still then a small error if you would take somewhere this point, but this would be somewhere single-digit picoseconds and maybe not that important. But of course, if you want to produce the best possible ultra-wideband product, then we have also getting a point further, and we have analyzed the tolerance of our phase center, best described with the sigma of phase center. The sigma of phase center describes a sphere where we are saying the phase center will be somewhere in this sphere. Everything has a tolerance. Our phase center has it also. And we have tested it. Luckily, as Roda and Schwarz, we are a company with rich knowledge, with antennas and shielding chambers, and are happy to can provide this kind of data. We can see for the frequencies 6.5 gigahertz and 8 gigahertz, we have somewhere a diameter for this sphere of 5 millimeter. This information is then also valid for plus minus 50 degree bore side antenna and DUT, of course. As you can see, it is difficult to find all the parts in the signal path and therefore being able to take them into the algorithm. We, Roda and Schwarz, are competence carrier, especially when it comes to an OTA setup with our rich knowledge and portfolio of shielding chambers and antennas. So feel free to contact us. But enough of the theory now, let's jump into the demonstration. Now we can see the graphical user interface from CM Squares, which is displaying the measurements. So symbol jitter, chip jitter, normal size cross correlation, the pulse mask can be seen here. For more details, again, we have a previous webinar. But the most interesting part is the power versus time window. We can see that we have exchanged 3 messages between DUT and our tester. So it's a double-sided two-way ranging procedure. The first one came from the DUT, the second one from our tester, and then again the third one from the DUT to our tester with the information about frequency error and also the T-loop time from the DUT. For this, we are using a special measurement mode, the Multi-Ppdu mode. This allows us to capture up to 20 milliseconds every message exchanged between our tester and the DUT. On the right side of our monitor, we can see the simple GUI from our WMT sequencer. And it's displaying here the values for our time of flight procedure. So the first one is the R marker from the DUT. It came with the timestamp of 73,000 nanoseconds. The second R marker is the one that was sent from our instrument to the DUT with a delay of 4 milliseconds. So this is also the reason why this number is much higher than that. Here we can see the value for the frequency error, which is also very important to take into account. And here we can see the bit stream, the hexadecimal bit stream of the information for the T-reply value of the DUT. Here we can see the T-reply, so the decoded from the bit stream, and then the calculated time of flight between these R markers. And we have performed this measurement in our shielding chamber TS7124, and this has roughly a distance of about 10 centimeter. As you can see, I can also restart this measurements, and it will be somewhere around 10 centimeters. With this, I finalize my part. I hope you could learn something and pass back to Martina for the conclusions.
Great presentation, Nico. Thanks. So let's proceed. So what are the takeaways from today's webinar? First of all, a digitalization enables a new user experience in the automotive. One is the future car access, which goes digital based on seamless smartphone integration. Multi-car access, key sharing, or even configurable driving rights for car sharing are such future topics. For testing of ultra-wideband devices besides regulatory requirements, the performance and interoperability aspects as addressed by the Fiera Consortium, the Ultra Wideband Alliance, and the Car Connectivity Consortium are of high importance. Concerning test requirements, the following topics are important to consider. First of all, testing ultra-wideband devices at very low power require test solutions able to generate and analyze very wide signals and need to have the required dynamic range. Here we are talking about an analysis bandwidth according to the ultra-wideband channel of about 500 megahertz, a very low signal power of maximum minus 41.3 dBm per megahertz, a receiver sensitivity in the range of minus 90 to minus 110 dBm. In addition, transmit power and antenna delay are very crucial parameters for ranging that needs to be calibrated. Finally, accurate time of flight measurements require verification. An accurate verification is guaranteed with our signal generators and signal analyzers as well as oscilloscopes, which are dedicated for testing in the development phase. The CMP200 as fully integrated purpose-built radio communication tester is perfect for solving the full spectrum of ultra-wideband test requirements, from chip development to device testing in production. So, Rohde & Schwarz collaborates with leading industry partners to provide excellent ultra-wideband test solutions, ensuring consistent device-to-device performance based on IEEE 4Z standard. Finally, let me summarize what Rohde & Schwarz is offering to test ultra-wideband. Let's start with the signal generator. The SMW200A is a high-end instrument that supports all ultra-wideband bands. The SMM100A is a mid-range vector signal generator covering up to 44 GHz, and it's also suitable to test ultra-wideband. The spectrum analyzer, FSW26, is a perfect solution for the development and verification of chipsets, modulators, and amplifiers supporting ultra-wideband. Our RTP oscilloscopes serve as wideband FR front-end and can directly acquire ultra-wideband FR signals without any need for down conversion. We recommend to use FSW and RTP with dedicated Rohde & Schwarz VSE software. You can use it either on your desktop or via the cloud. In the entry class, we offer also different devices like the RTM300, easy upgradable FPC spectrum analyzer, as well as very suitable power supplies. If you look at the communication tester, the CMP200 is a compact, non-signaling tester that's perfect for solving all ultra-wideband challenges. It allows complete HRP, ultra-wideband TX and RX measurements, and for RX measurements, either customer waveforms or waveforms generated by Rohde & Schwarz WinIQ Sim 2 simulation software can be used. Finally, of course, we also have very suitable shielded chambers for ultra-wideband like our CMQ200 and the TS7124. If you have questions, please come back to our product managers or to me. We hope this was a valuable webinar for you. From the entire team behind it, thank you for having placed your trust in Rohde & Schwarz.
네, 여러분 잘 보셨죠? 자, 이제 Q&A 하면서 여러분 오늘은 이제 추석 전 마지막 토크하이트 방송이니까 5시 10분까지 할게요. 10분까지. 오케이? 바쁘신 분은 나가셔도 되고 지금 설문하고 있으니까 설문하시고요. 네. 박조영님께서요. LOS 환경에서 높은 정확도를 유지한다고 하면 실제 차량에서 UWB 통신을 사용했을 경우 NLOS일 경우가 많을 텐데 해당 상황을 극복하는 방안이 있을까요?
UWB 기술은 펄스 신호를 사용을 하기 때문에 상대적으로 NLOS일 경우에도 좀 강력한 그 방안을 가지고 있습니다. 펄스 신호라는 것 자체가 거기에 관한 이제 좀 방안이 되는 기술입니다.
네네. 이준수님, UWB 동작 주파수가 높고 장애물 투과 우수성이 높은 만큼 인체에 대한 유해성은 어떤지?
인체의 유해성은 저도 확인을 한번 해보겠습니다.
이게 장애물 투과성이
네,
높죠.
네.
좋죠. 손정환님, 광대역 신호기 생성은 어떤 장비를 사용하는가요? 범용 장비 업체가 있는지요?
일반적인 저희 로데슈바르즈에서도 지원을 하고 대부분의 장비는 흔히 이제 TX 신호를 측정을 하는 이제 스펙트럼 계열이 있고 그리고 신호를 생성을 하는 그 신호 재생기 제너레이터 장비가 있습니다.
네네.
그래서 그런 범용 장비 업체는 뭐 저희 로데슈바르즈뿐만 아니라 다양한 업체들이 있습니다.
이양성필님, 다양한 리모트 킬리스 엔트리 기술에 따라 적절한 테스트 솔루션 요구사항도 다를 수밖에 없을 텐데 이런 무선 기술 중에 UWB의 지원을 포함한 맞춤형 테스트 솔루션은 어떤 특장점을 가지고 있는지요?
UW를 비롯한 이제 다양한 이제 무선 기술들은 그 기술을 관리하는 표준이 다 있습니다.
네.
흔히 이제 UWB 같은 경우는 아까 이제 제가 언급해 드렸던 것처럼 IEEE의 802.15.4G를 기준으로 표준이 지금 사용이 되고 있으며 그 표준 안에는 어떠한 항목을 어떤 값으로 측정을 하는 테스트 솔루션들이 다 나와져 있습니다.
네. 김승주님, 전기차 구동 시스템의 PWM 파형 분석에도 적용이 가능한지요?
제가 이건 답변을 드렸는데
네네.
이 내용은 저도 확인을 하고
네네네, 알겠습니다. 자, 나머지 여러분들도 답변을 많이 주셨거든요. 답변 체크해 보기 바라고요. 그 양정수님, 이게 EMC 테스트 되는 거예요?
네, 그가 EMC 같은 경우는 이제 인접 신호에 이제 전자기 신호가 이제 나오는지 안 나오는지를 보는 내용인데.
네.
기본적으로 UWB 신호는 그 이제 1메가 기준으로 마이너스 41dBm을 쓰고 이걸 500메가 대역으로 하더라도 마이너스 13dB 정도의 파워를 사용하기 때문에 상대적으로 영향을 덜 줄 수밖에 없고요.
네.
그래서 기존에 측정하시는 EMC 방식과 뭐 동일하게 테스트는 되지만 기본적으로 레벨 자체는 상당히 이제 낮게 되는 거죠.
네. 그래서 이지영님께서 요거 EMC 시험할 때 그 TX를 강제로 써서 RX를 받는 시험을 하는데 설명하고 있는 제품은 RX나 TX를 제품에서 쏘고 측정할 수 있는 제품인지요?
네. TX랑 RX랑 다 같이 측정할 수 있습니다.
네. 이종우님, 저전력에서 잘 작동하는지요?
네. UWB 기술 자체가 기본적으로 저전력에서 이루어진 기술이라서 잘
네네.
됩니다.
자, 나머지는 이제 다 답변을 체크해 보시면 되겠고요. 어떠세요? 매진 이 UW 기술이
네네.
앞으로 어떻게 발전할 것 같아요? 그냥 개인적인 의견, 그냥 편하게.
네. UWB는 항상 그 인프라 문제가 가장 단점으로 대두되었었는데 삼성이나 애플이나 뭐 이런 큰 대기업들이 이제 투자가 이루어질 거기 때문에 당연히 이제 인프라 문제는 해결이 될 거고요. 그러면 투자만큼 이제 다양한 어플리케이션이 나올 거라고 예상이 됩니다. 근데 대부분의 이제 측이 기술을 사용한 이제 핸즈프리 또는 뭐 도어락, 디지털 키 이런 그 인도 내비게이션을 활용을 하는 기능들이 이제 많이 활용이 될 거고 추가적으로는 이제 VR이나 AR에 관한 앵커 기술들도 사용이 될 겁니다.
얘가 VR, AR하고도 연동?
그러니까 VR이랑 AR이라는 기술 자체는
네.
기본적으로 이제 정확한 측이 기술이 기반이 되어야지 지원을 할 수 있는 기술이다 보니까.
그렇네, 진짜.
기존에 뭐 사용되시던 포켓몬고나 이런 거는 뭐 몬스터가
그렇죠,
이상하게
그렇죠,
나오는
그렇죠.
형들이 있죠.
그렇죠,
위치를
그렇죠.
못 잡으니까. 근데 UWB는 정확한 측이 기술을 가지고 있기 때문에 AR이나 VR에도 당연히 좋은 기술이 됩니다.
더 리얼하겠네.
그렇죠.
자, 어쨌든 간에 그럼 이것이 이제 좀 더 우리 실생활에서
네네.
더 많이 볼 수 있는 그런 때가 한 몇 년 뒤쯤에 오리라고 보십니까? 지금 같은 이런 추세로 간다면.
이런 추세로
항상
간다면
보면 매니저님은 이런 새로운
네네.
프로토콜이나 새로운 기술들이 어떻게 확산되는지를 쭉 봐오셨잖아요.
네네.
우선 기술들이.
네.
그런 이제 경험해 봤을 때, 네.
기본적으로는 벌써 나온 제품들이 있기 때문에 그리고 뭐 투자가 이루어진 상태이기 때문에 뭐 한 3, 4년 이내에는 어느 정도 저희가 실생활에도 주위에서 볼 수 있는 환경이 충분히 될 거라고 생각이 됩니다.
네. 그 3, 4년 내에는 그러면 이 UWB를 활용한 다양한 서비스들이 많이 나오겠군요.
네, 지금은 어차피 지원되는 뭐 핸드폰 자체도 갤럭시에서 최신 계열이나 몇 개가 안 되지만
네네네.
향후 나오는 모델들은 점점 많아질 거니까 당연히 어플리케이션도 많아질 것이라고 생각이 듭니다.
네. 지금 윤정원님께서 왜 그동안 그러면 이렇게 포텐셜이 많은 기술인데 왜 그동안 이게 지지부지했는지.
그러니까 그동안 아까 이제 말씀드렸던 것처럼 UWB라는 칩셋사는 기존의 와이파이나 이런 거 대부에서 인프라가 너무 적었던 거죠. 그만큼 그 모든 기술은 투자가 되는 돈이 있어야지 환경이 생기는데 UWB는 이제 인프라가 너무 적었던 거고, 근데 그 인프라 문제가 지금에 있는 이제 양대 산맥인 애플이나 삼성 또는 뭐 중국에 있는 샤오미까지도 투자가 이루어질 거기 때문에 그 문제가 해결이 되면 당연히 이제 다양한 어플리케이션이 또 생성이 되는 거죠.
네. 참 보면 진짜 이 기술이건 비즈니스건 다 때가 있는 것 같아요. 그죠? 스티브 잡스도 예전에 잘 안 되다가, 그쵸? 딱 이게 때가 되니까 확 한 거죠. 때가 참 중요한 것 같아요. 자, 여러분들 오늘 여기까지. 오늘 어떻습니까? 이렇게 질문 이렇게 쭉 보시면서 어떤 생각이 드셨어요? 네.
뭐 이런 게 처음이라 질문 올라오시는 게 뭐 흔히 말하는 낮은 레벨부터 네. 높은 레벨의 질문까지 다 들어와서 엔드투엔드로 좀 순간적으로 당황할 때도 있었는데 네. 좀 더 이제 많은 도움이 될 수 있도록 노력하겠습니다.
네. 봉송아님께서 블루투스도 처음에는 굉장히 정말 지지부진했었나 봐요. 그렇죠. 근데 무선으로 오디오를 사용하는 애플이 나오면서 대박이 터졌다고.
그렇죠.
아, 진짜 그렇네.
블루투스도 그 클래식이 나오면서 걔는 이제 이제 보이스까지 처리를 하게 되면서 이제 활성화된 거고, 그 뒤에는 최근에는 이제 뭐 저전력을 위한 LE 기술이 추가가 되면서 또 뭐 웨어러블 기기 쪽으로 또 옮겨가기도 하는 거죠. 네. 기술이 이제 다양한 어플리케이션이 생성이 되면 기술이 이제 그때그때 때마침 나오게 되기도 하고 어플리케이션도 나오게 되는 거죠.
UWB가 대박 나면 로데슈바르즈도 대박 나는 겁니까? 아니 메이저면 대박 나는 겁니까?
대박 나도록 노력해 보겠습니다.
네, 자 여러분, 어떻게 보면요 여기 우리 토카이티에서 IT 많이 했지만 사실 이게 이런 전기전자 쪽이 딱딱한 것 같지만 어떻게 보면 훨씬 소프트웨어 분야보다 전기전자 쪽이 굉장히 더 리얼한 것 같아요. 구체적이고 더 어떻게 보면 더 굉장히 그래서 어떻게 보면 더 상상력을 더 자극시키는 또 것도 있어요. 어떻게 보면 이게 어떻게 소프트웨어가 더 그럴 것 같지만, 그래서 사실 이런 것도 앞으로 더 많이 좀 저희 토카이티에서 많이 좀 해서 모셔가지고 이런 거 하면 좋을 것 같아요. 여러분들 뭐 저희 토카이티 팬들 웬만한 분야 다 커버할 수 있는 분들이니까. 네. 매니저님도 저희 시청자분들께 추석 인사 좀 하시고 마치는 걸 하죠. 네.
명절 건강하게 잘 보내시고 다음에 뵐 기회가 있으면 좋겠습니다. 감사드립니다.
네, 알겠습니다. 네. IT 전문 방송 토크IT에서 테크 분야별로 짧고 진한 시리즈 영상들을 편하게 골라서 보실 수 있습니다. 구글이나 네이버에서 한글로 토크IT 치시거나 토크IT.tv 사이트로 오시면 됩니다.